Hey everyone, I hope you're doing well today. In this video, I'm going to be talking about related rates. If you plan on taking the AP Calculus exam, these types of problems are definitely good to know. Throughout this video, I'm going to cover a few different examples on problems involving related rates. Now you'll know you're dealing with a related rates type of problem when you're given this type of information. First, you'll see that you have an equation that's going to have two or more variables. Okay. After that, you always want to see if your variables are going to change with respect to time. That's very important. And third, you're going to see that you're going to use derivatives to link the rates of change between the different variables with respect to time. Throughout this video, try to be mindful and see if you can identify these three types of information in each of the problems. If you find any value from this video to help you prepare for your exam, I'd really appreciate it if you could give this video a like and even consider subscribing. I encourage you to grab some paper, something to write with, and let's do some math together. Alright, so here's the first question. A 25-foot long ladder is leaning against the wall and sliding towards the floor. If the foot of the ladder is sliding away from the base of the wall at a rate of 15 feet per second, how fast is the top of the ladder sliding down the wall when the top of the ladder is 7 feet from the ground? First, it's important to know that we have a 25-foot long ladder and it's leaning against a wall and sliding towards the floor. The foot of the ladder is sliding away from the base of the wall, and the rate at which it's sliding across the floor is 15 feet per second. That's one of our rates. The question actually asks us how fast, which is asking us for a rate, is the top of the ladder sliding down the wall when the top of the ladder is 7 feet from the ground. Now, if you can draw a picture, I totally recommend that you do so. So I'll draw a horizontal axis here representing the ground, and I'll draw a vertical axis representing the wall. So I'll label the ground right down here, and I'll label the wall right over here. We know we have a ladder that's leaning against this wall and touching the ground, and it is 25 feet long. The ground and the wall meet at a 90-degree angle, so that's perpendicular, and this we'll label as our vertical distance, or y, and we can label this over here as our horizontal distance, or x. And just so you understand the two types of rates we're trying to relate here is that the top of the ladder is actually sliding down the wall, while the bottom of the ladder is sliding across the ground. So those are the two rates that we're looking at. Now that we have a picture and you can see that the top of the ladder is sliding down while the bottom of the ladder is sliding to the right, let's see if we can write an equation. Now when you're thinking of an equation to write, I hope your first instinct is to go ahead and write the Pythagorean theorem since we have three sides and we have a right triangle. So we can write x squared plus y squared is equal to 25 squared. And now that we've established an equation that we can work with, let's take the derivative of it with respect to time, or t. We can go ahead and write the following. So the derivative of this x squared is going to be 2x times dx dt. The derivative of this y squared is going to be 2y times dy dt. And the derivative of this constant is just going to equal 0. Now, since the question is asking us how fast is the top of the ladder sliding down the wall, we actually are going to be looking for this dy dt. This represents the rate at which the vertical part is changing. Now at this point, it's important to make sure you understand that dx dt just represents how much it's changing in respect to the x-axis, and this dy dt is letting us know how much this ladder is changing in respect to the y-axis. Because the question is asking us how fast is the top of the ladder sliding down, we're going to be looking for this dy dt. This needs to be isolated. Now, since we're told in the problem that the base of the ladder is sliding away from the wall at a rate of 15 feet per second, that 15 is really what we're saying is the dx dt, or the rate of the horizontal change. Now, another piece of information that we haven't actually used yet is the fact that the ladder is currently 7 feet from the ground. Using that information, we can go ahead and say that this y value, this y, is equal to 7. Plugging in this information into our equation, we can say that x squared plus 7 squared, or y squared, we just substituted it in, is going to equal 25 squared. Going ahead and using the Pythagorean theorem, we can see that when the height of the ladder was 7 feet from the ground, the horizontal distance from the wall was equal to 24 feet. Plugging in the 7 we were given in the problem for y in this location, and the 24 that we just found out from the Pythagorean theorem right over here for x, we can write the new equation as So going ahead and multiplying this 2 times 24 times 15, that's going to equal 720. And then going ahead and multiplying this 2 times 7 together, that's going to be 14. So we can write 14, and then we have a dy dt, and that's equal to 0. Now just to make a little bit more room, I'm just going to take this part up here and just make it a little smaller, put it off on the side, and I will take this bit of information and just drag it up so we have a little bit more room to work with. Subtracting 720 from both sides, we can say 14 times dy dt is going to be equal to negative 720. Now finally, dividing both sides by 14, we can say that dy dt is equal to negative 360 over 7. This right here represents our solution. So taking a step back and trying to see the big picture here, we know that the 25-foot ladder was 7 feet off the ground when it was 24 feet away from the wall. Additionally, the two rates that we're trying to compare is the top of the ladder sliding down the wall and the rate of the bottom of the ladder sliding away from the wall. At the exact moment when the ladder was 7 feet off the ground and 24 feet away from the wall, we knew that this ladder was sliding away from the wall at a rate of 15 feet per second. This was one of our rates, which is denoted by dx dt, or the rate of change in that horizontal distance in respect to time. And we went ahead and used all that information and plugged it in to find out dy dt, which is how fast the ladder was sliding down the wall at that time with respect to time. Hopefully it makes sense that since the ladder is sliding down the wall, that we have a negative rate of change here in our answer. This ladder is sliding down the wall at a rate of negative 360 over 7 feet per second. Let's try another one. Suppose we have a spherical balloon and it's expanding at a rate of 60 pi inches cubed per second. The question is, how fast is the surface area of the balloon expanding when the radius of the balloon is 4 inches? So let's start with a few key pieces of information. First, we know we're talking about a sphere, that's the shape, and they give us a rate of 60 pi inches cubed per second. So they're giving us a rate, but they're also asking us how fast is something happening, about another rate. They're telling us to use surface area, that's maybe another formula. It's expanding when the radius, they're telling us a given measurement at a given time. Now, because they give us this 60 pi inches cubed per second, we know we're talking about some sort of volume, so we're going to need a formula here. To find the volume of a sphere, it's important to know that volume is equal to 4/3 times pi r to the third power. So while we have a rate given for the volume, we also are going to have a rate dealing with surface area. So since we're dealing with surface area, we'll need another formula. To find the surface area of a sphere, that is going to be area, or surface area, is equal to 4 times pi times r to the second power. So it's really important to understand that we do have a radius here as a variable in our volume formula, and we also have the radius in our formula for surface area. So while we're given a rate of change for the volume, which is going to be 60 pi inches cubed per second, we're not given a rate of change for the area, or the surface area. When the question does ask us about how fast, that's what we're looking for. We're looking for the rate of change for the surface area of this sphere. With respect to time, this value over here is our rate of change for the volume, and that's going to be our dv dt. And the rate of change for the surface area we're looking for is going to be dA dt in relation to time. Now that we've organized the information that we're given, we really have two equations that we could choose from to get started. Now, since we don't know this rate of change for the surface area, I think it makes more sense to start with this top equation dealing with the volume. Starting off with volume, let's take the derivative of this equation with respect to t. When we do so, we're going to get looking at this dv dt, keep in mind that that is just going to be the rate of change for the volume, so we can substitute this in for 60 pi. So we'll take this part right over here, and I'll just write that in that this will be substituted in for the value of 60 pi. And to continue substituting, remember that we're told that this is all happening when the radius is equal to 4, so let's just take this radius right over here and substitute in that value for 4 right in for r as well. Substituting in, we'll get 60 pi is equal to 4 pi times 4 squared times dr dt. Cleaning this up a bit, we can then get 60 pi is equal to, and if we say 4 squared is 16, 16 times 4 is going to be 64. we can say this is 64 pi times dr dt. Dividing both sides by 64 pi, we can then go ahead and write that dr dt is equal to 60 pi over 64 pi. Dividing top and bottom by 4 pi, we can say that dr dt is simplified down to 15/16. This just lets us know that the radius is changing at 15/16 inches per second. Now that we have this dr dt, we can actually solve this problem. Let me tell you why. So try to recall that we already had the formula for volume, and we also had the rate of change at that moment. We had the formula for surface area, but we didn't have the rate of change yet. Because the two things in common for these two formulas deals with their radius, right, or their radii, we had to find out what this dr dt was, because that's going to be the link between these two formulas. Now, just to clean up a little bit of space here, I'm just going to delete all this work that we did to find our dr dt, and let's just place this dr dt off on the side and use it in just a moment. Now it's time to take a look at this surface area formula. So we have area is equal to 4 times pi times r squared, and if we take the derivative of this equation, we will get this. So the derivative of a is just dA dt, and the derivative of this 4 pi r squared is going to be 8 pi r dr dt. Now for this dA dt, we're going to leave this alone for now, because keep in mind that's actually what we were looking for, because we needed to know the rate of change of the surface area. As for the radius at this given moment, from before we said it was 4, and that's still true, so we'll say a 4 is going to go in for r. And as for this dr dt, well, we spent all that time earlier finding dr dt that was equal to 15/16, so we can make another substitution here. So in for this dr dt, we will substitute in 15/16. Substituting these values in, we can get dA dt, which is ultimately what we're looking for, is equal to 8 times pi times 4 times 15/16. Cleaning this up a bit, we can say that dA dt is equal to, well, 8 times 4 is 32, and 32 will cross cancel with a 16 to make 2. 2 times 15 is 30, so we're just going to get 30 pi on the other side. Now, because this dA dt really just represents the change of the surface area in respect to time, this is going to be measured in inches squared per second. So when the question was asking us how fast was the surface area of the balloon expanding when the radius was equal to 4, we know that it's changing by 30 pi inches squared per second. Now for some key takeaways here, we started off with this volume formula because we were actually given a rate to work with, so we had more information. And once we found out the rate, or dr dt for the radius, that was useful when we went ahead and used this surface area formula, right? Finding that information and plugging in all of the things that we found, we were then able to substitute and find dA dt, and that is the rate of change for the surface area at that given moment when the radius was 4 inches. Here's the third and final example of this video. A boat is being pulled towards a dock by a rope attached to its bow through a pulley on the dock 7 feet above the bow. If the rope is hauled in at a rate of 4 feet per second, how fast is the boat approaching the dock when 25 feet of the rope is currently out? So I'm going to start by drawing some sort of picture here to help you visualize what's going on, to help myself visualize it as well. So I'm not very good at drawing, but I'll draw a dock, maybe something that looks like this so far. And the dock is going to be resting up here, and just to give you some understanding of where I'm thinking the water is, I'm thinking the water is right around here, something along those lines, and we have some sort of pulley system, right? So I don't know, maybe I'll draw like a little type of structure here, and I'll go ahead and draw some sort of rope coming out of this pulley where the boat is going to be in the water. So again, like I'm not really much good at drawing, but maybe I can draw some sort of a boat like this, and I'll label it as the boat so you are convinced. Look at that. Beautiful. All right, there's my drawing. So we're told in the problem that the rope is going to be attached 7 feet above the bow, so that's actually going to be this measurement right over here. So I'm going to go ahead and label that in, and this height here is going to be 7, from the top of the pulley to the height of the bow. I'm going to go ahead and use R to represent the length of the rope. And to represent the distance of the boat to the dock, I'm going to use the letter B for boat to represent that distance right over here. Now just going ahead and redrawing this triangle on the side to clean it up just a little bit to give you a better or more clear picture of what's going on, we really have this 7 over here. We have a distance of b on the bottom, which we don't actually know, and we have a distance of r, which is the length of the rope, over here on the hypotenuse of the right triangle. Now we're told that the rope is being hauled in at a rate of this 4 feet per second. So relative to time, or respect to time, we can say that we do know that dr dt, let me go ahead and write this down, that dr dt, the distance of the rope or the length of the rope, the rate that it's changing, is going to equal -4, right? As the boat's being pulled closer and closer to the dock, then the rope length is going to be decreasing over time. So it's going to be a negative value. So we know one of the rates that we're dealing with is dr dt. That's the rate of change of the length of the rope. And we're going to have to also deal with the rate of change of the boat as well. And I'm just going to go ahead and write that right now. That's going to be db dt, as the boat's getting closer to the dock. Now we have a bunch of information, but we actually don't have an equation to work with just yet. So hopefully you can see that because we have a right triangle, we can maybe use the Pythagorean theorem and say that b squared plus the 7 squared, right, is going to be equal to the r squared, or the rope length squared. So we can go ahead and write that as an equation to begin with. Now going ahead and taking the derivative of this equation, we can then write the derivative of this b squared is going to be 2b times db dt. The derivative of this 7 squared, which is a constant, is just 0. And then the derivative of this r squared is going to be 2r times dr dt. Dropping the 0 and simplifying this a bit, we can say that this is going to be 2b times db dt. And we can say this is equal to the 2r times dr dt. Now that it looks like we kind of did everything that we possibly could so far, keep in mind that this whole thing is happening when the rope length is 25 feet. So at this point, I think it's a good idea to say, okay, this rope length here is actually 25 at this given point. So the hypotenuse here we can say is 25. And then we can just go ahead and, looking at this equation, we can make a quick substitution and say this is 25. Now I waited for this time to do it just because it's important that you make these substitutions after you take the derivative. Make sure you don't do it beforehand because it gets things a little bit weird because things will be changing. So this is just one particular case. So make sure you plug in this 25 or this rope length after you take the derivative and then make that substitution. Now another substitution we can make is the fact that we know that dr dt, this piece right here, is the rate of which the rope is changing. And we already knew that dr dt was equal to -4 because the rope length is going to be getting shorter and shorter as the boat gets closer and closer to the dock, right? So we can go ahead and take this length of -4, which is going to be the rate of change of the rope, and say that this dr dt is going to be -4. Now if you look at our equation, we still have two unknowns here, right? We have b and we have db dt. B is just the distance, but dB dt is telling us how fast the distance is changing. So when the question does ask us how fast is the boat approaching, that means that we must be able to know what this B value is, or else we can't really solve for dB dt, which is our true unknown. Now, going ahead and looking at our right triangle, if we know that the R is 25 and this value is 7, or the vertical distance, we can just use the Pythagorean theorem to solve for B. Using the Pythagorean theorem, here's my work for solving for the value of the letter B. Now that we know that the value of B is equal to 24, let's go ahead and plug that in to our equation. We can say that B equals 24. Just to clear up a little bit of space to finish this problem, let's just get rid of this and let's simplify this equation. Now just to get a little bit more room to continue this, we can now make some substitutions and write 2 times 24 times the dB dt, the rate at which the boat is approaching the dock, and that will be equal to this 2 times the length of the rope, which is 25, times the -4, because the rope length is getting shorter. Now to isolate this dB dt, we can divide both sides by 2 times 24, and this whole thing is going to equal 2 times 25 times the -4, put that in parentheses again, that's going to be all over 2 times 24. These 2's can cross cancel, and this 4 and 24 can make a 1/6. And finally, simplifying this down, we can say that dB dt, the rate at which the boat is approaching the dock, is equal to negative 25 over 6, and that's going to be feet per second, I believe. Hopefully it makes sense that our answer is going to be negative here, because as the rope is getting shorter and shorter, this boat is going to get closer and closer to the dock. And that wraps up this video on 3 practice problems on related rates for calculus. If you found this video helpful, I'd really appreciate your kind words in the comments. You can even consider giving this video a like, and maybe even subscribing for future videos. If you're taking your exam soon, I wish you the best of luck, and as always, keep up the great work, and I'll see you in the next one.